Thank you. First of all, welcome to everybody. We see 10 attendees. Thank you very much. Emilia, Correia, Shreedevi, and Nicolas Bergeot will share this first slot. Thank you.
Good morning. Good morning, everybody. Nice to have you participating in our session in radio. Let's see. In the radio science for Arctic and Antarctica from atmosphere and geospace parallel session. You are welcome. The speakers will have 10 minutes, 12 minutes for presentation, 3 minutes for questions. Questions can be asked using the Q&A and chat box function in Zoom screen. This session will be recorded, and please visit our posters in the poster exhibition space. Okay. Let's waiting. We have only Ryan online at this time. Giorgiana, I think we need to wait for the Nicolas will start presentation about the radio science research on Antarctic atmosphere. Please, Nicolas, you can start your presentation, okay?
Okay. Just wait a few minutes, please. Okay, hello everyone. So let me present a proposed scientific research program planning group in the frame of SCAR. So the presentation is called Radio Science Research on Antarctic Atmosphere, but it's going to be more large than the title we wrote there. I'm presenting in the place of Lucia Alfonsi from NGV, which is not here. She's in Boston at the Beacon Satellite Symposium. So, and the other people, there are a lot of people also contributing to this on behalf of the Resource Planning Group core membership. So Resource is a physical science and geoscience sharing program planning group within SCAR, which stands for Radio Science Research on Antarctic Atmosphere. But we recently changed last week the name of this planning group to Agatha. So this is a new mail for all the people which resource. So now you have to forget resource and to think about Agatha, which stands for a more large subject about Antarctic geospace and atmosphere research. So the aim of Agatha is to gather communities that investigate the polar weather and geospace with a particular focus on Antarctica, but with a bipolar perspective. And the scope is to monitor the polar atmosphere physics to better monitor and to better investigate and better understand all the physics. So when I speak about atmosphere, it's neutral and ionized atmosphere. When I speak about, well, you all know for sure, but for the new people, if there are new people here, the first, the ionized atmosphere is the ionosphere mainly, and the plasmasphere also, which is equal to the ionosphere. And for the neutral atmosphere, we think about the thermosphere and also the troposphere. And we also take into account for the magnetosphere, which surround all these layers. The scope also is to contribute to the better understanding of the Sun-Earth interactions, and also to support scientists which are interested to remove or mitigate atmospheric noise to their observations. So the goal, what is in the frame of Agatha? The first is to, as I said, to monitor, investigate, and better understand the polar atmosphere physics. This is an open question that has been identified, some open questions, sorry, which have been identified in the first SCAR Antarctic and Southern Ocean Science Horizon Scan. This is a question. So the question 71 where the goal will be one of the main objective is to better understand the coupling between the ionosphere and the neutral atmosphere and their interhemispheric symmetries and asymmetries. Question 72 is the assessment of the impact of the polar atmosphere on the technological and humans ground level. And what is the link, for example, for telecommunication, for GNSS observations, etc., etc. And the third question is to investigate the impact of atmospheric waves and their role in the vertical coupling between the upper and lower atmosphere. The second point is to better understand the Sun-Earth interactions. This is in the conclusion of the SCAR strategic plan for 2017 to 2022. If they push to international collaboration to expand and to understand this link between Sun and Earth for Antarctica and also for astronomy observations and Earth outer atmosphere observations, link it to the magnetosphere, outer space, and Sun-Earth interactions. The last point is to support, as I mentioned just before, is to support the sciences, the instrumental people which are need to remove or to mitigate the atmospheric contribution to which affect their observations. And this is in the 6 priorities from the Antarctic Science, which has been published in 2014 by Kennicott. And for that, they push us to work together and to coordinate international efforts. So what are the main tools that we have within Agatha? It's a huge amount of different data sources, such as Ionoson, SuperDAN, Hyometers, GNSS receivers, GNSS tech dedicated and situation monitors dedicated receivers, VLF observations, high power large aperture radars, SCAT data, all sky view imagers, geomagnetic observatories. So all these instruments permit to monitor from the low atmosphere to the magnetosphere, magnetopause, actually, and magnetosphere, to better understand this geospace environment and also the neutral atmosphere. When I speak about neutral atmosphere, it's mainly for the integrated water vapor, which is one of the main greenhouses that we have on Earth. So this is for that we launched an initiative 2 years ago to write a review paper in the frame of resource for Agatha, sorry, and previously with the GRAPE expert group. So here is a map of all the data that we have now. I didn't put all the instruments in them, but there are all the instruments that have been described in the last slide, the previous slide, sorry. So we have quite a huge amount of data, ground data, and we don't show here, but we also have a lot of satellite data. So it's a huge amount of data. And the goal of Agatha is to enlarge our community, which come from GNSS to all these instruments. And for that, we are writing a paper which is from Alfonsi et al. It's presently under review after minor revision, so it's accepted actually in surveys in geophysics. And we use all these data sets to first, I'll just highlight some points here, to study the long-term properties of neutral and ionized atmospheric layers. So here on the left is an example of the long term, it's 15 years of precipitable water vapor that we have from one GNSS station here. So we can start to make some climatology of this integrated water vapor. Here is for the ionized layer, where we have the climatology of the ionospheric scintillations from one station in terms of sigma phi and S4 parameters. We also the multi-instrument studies of extreme events. An example of 2019 event where we are showing the magnetic data from a ground station here. We are also showing some VTEC time series, so it's doing less than 1 day here for 8 hours between 10 and 11 May of 2019. We also have some ROTI data, so the correlation between the geomagnetic decrease anomaly, sorry, and the Roti anomalies also, and the scintillation data of sigma. And we also, to show you what we can do, is that in correlation we use all sky imager data, where you can see here an increase of photo emissions at the same time that one of the peak of this event. Sorry. We still need to have some answer to several questions. I won't go details here, but we have some question about the effect of the verticality of the geomagnetic field at this high latitude, and how this can explain the electric field penetration at to low latitude. We also are looking for different asymmetries between the north and the polar regions during solar perturbations. We also want to better understand the role of coupling between the neutral and ionized layers. We also are interested in the plasmaspheric erosions. What is it really a signature of electric field penetrations during geomagnetic storms? We are also looking for the small structure to high structure and high structure to small structure, so fragmentation of the structure in the ionosphere during stormy periods, such as the tongue of ionization, which can lead to lower scale ionospheric distributions, for example. We would like also to understand the origin of long-term behavior of the polar ionosphere and to see what is the effect of the natural and anthropogenic contribution to such changes. And also we want to model, to better modeling the coupling between the neutral and the ionized atmosphere at high latitude. I will pass this because I don't have the list of the people which are the co-members of Agatha program. So it's about 30% from different countries which are acting into this in this proposal, in this project. But yeah, I have to say that Agatha, if it's accepted by the SCAR delegates, will embed the expert group, which is called GRACE, that we more or less all knows. I hope. We have a presentation this afternoon at 1:30 UTC on this expert group. And to come
Nicolas,
back to Agatha, yeah, I finished.
You have 2 minutes.
Yeah, well, I'm finishing in 30 seconds. Okay. Just to let you know that the physical science group, we had a meeting last week, business meetings in physical and geoscience groups, and the physical science group will recommend Agatha proposal for, as a planning group to the SCAR delegates for funding. So this is a hot news from last week. And so we have to wait now September for the acceptance from the SCAR delegates. And here finished. Thank you for your attention. If you want to participate, sorry, if you have any questions about Agatha, you can contact Lucilla at this address or myself at this address, email address. Thank you for your attention. I'm open for questions.
Thank you, Nicolas. We have no questions till now. Then we go ahead. Let's see. Tahil Jayandra is already here. Nicolas, could you close your sharing screen?
Yeah. That's it.
Okay. Now we will have Tahil Jayandra talking about polar cap patches and airglow intensity variations, a comparative study with ionosonde. Could you start, please? Oh, she was here, no?
Jai, are you able to share your screen?
Yeah, he has sent a message that he is here. I think he is trying to connect. Oh, he says he cannot see the option to share his screen. So
He do not
like
have.
Carlton, can you?
IT team,
Yeah.
please. Can I ask that all attendees may have may,
Permission.
Now I can.
okay, thank
Oh,
you. Sorry.
So yeah, you didn't allow me to share the screen initially. Can you see my screen now?
Yes, we
Yes,
can
we can.
see.
Yes,
Okay.
yes,
Okay.
Gian.
Okay. So, sorry for the technical difficulties. I am also attending the International Beacon Satellite Symposium in Boston. So I thought I will come and join this and give the presentation. So there was a slide, and thank you for the opportunity to present this talk. There is a slight change in the presentation I was planning to give. Initially, I thought that I will be able to give you the comparison between between the patches we see optically and using radio instruments, but I was unable to complete the study during the time period. So anyway, I'm trying slightly changing the flavor, but the essence will be the same. So I'm going to, instead of focusing on the statistics, I'm going to show you a case of the patch and then discuss the implications of that in the broader sense. So I'm going to go through the patches introduction and a small, a short introduction and background, and then I will go and describe the event I was going at and what type of instruments I am using to study that particular case, and then results and then summary. So the patches, it's historically, it has treated as an enhancement of electron density in the nighttime, no production ionospheric scenario in the polar region. So in the polar region, during winters, it is dark, so there is no source of production, but we do see ionization enhancements in the polar region. So they call those enhancements in the ionosphere as patches, and they assume it is convecting from sunlight region to the polar cap and transported back into the night side ionosphere. So that is historically how the patch is described. However, with the recent development of or explosion of data availability in the polar region, we were able to gain a bit more understanding about the patch structuring and how they form, how they evolve, and how they eventually die. So, and patches, for all intents and purposes here, they are medium scale structures in ionization, a few hundred kilometers, give or take. And it can be measured using ionosondes or classically, historically to us, detected using ionosonde, and then optically, and then recently in coherent scatter radar and GNSS tomography. So if you could look at the screen, you will see that there are several cases. This is an old paper by Leroy and Steele and Cogger about the patches using optical instrumentation. You can see the enhancement in the electron optical intensity. And this is the other one is the tomographic technique that detected patches. But I would like to pay your attention to the one above that, where that is an ionosonde detection of patches. On top of that, I plotted the intensity of auroral emission at 6300 nanometer. That is formed due to through the dissociative recombination. So you can see one-to-one correspondence between the enhancement in the electron density, which is expected, and the 630 nanometer emission. And On the right hand, you can also see small scale patches due to the solar wind magnetospheric ionospheric interaction, or you can call that alphanic reconnection. So these are the several ways to look at patches. And it has, as I said before, it has been studied historically. If you look at the literature way back in 70s, we started studying this. And then we still continue to study this, this feature in the ionization. So outstanding questions, formation mechanism, I said too many, it's not a problem, but if you are trying to understand the physical mechanism, and if you look at the philosophy of physics, too many mechanism does not bode well with explaining any particular phenomena. So it's, in a sense, it is a problem. Whenever you see a literature or read a paper on patch, everybody proposes a mechanism for the formation. But at fundamental level, there should not be more than one mechanism that, or one or two, depending upon the situation, that produces that patch. Also, electrodynamics, how the background ionospheric electrodynamics changes the structuring in the patches. Okay, so we have a high-speed convection in the polar region, and one would expect that will change the chemistry and the dynamics within the patch that produces further structuring within. And then the next question is chemistry. So that is, how does the chemistry affect the patch? And how does this enhanced ionization affect the neutral density and wind and the drag in the polar region? That is also an outstanding question. And eventually what we are trying to address is, does this patch contribute to the magnetospheric density budget? That is through ion outflow. So you have an enhancement in the density, that means you have more outflow, eventually populating the magnetospheric with ionospheric plasma. So that is the ultimate question. So I'm showing you some, in the bottom, some structures of the patch detected at Eureka in the Arctic. So here I'm showing you 4 panels. One is the range, group range at 4 megahertz for a period of almost 6 hours. So you can see a dense, if you look at as point of reflection of 4 megahertz signal, there is no group retardation, means the density is very high. And bottom of that, you can see the direction of E cross B drift. So basically it is in the anti-sunward direction during that period. So this is the patch period we are talking about, and that is the convection azimuth in the anti-sunward direction. And the panel below is the actual speed of the convection, or speed of E cross P, if you want to put it. So during the initial period, you have around 100 meters per second background flow. But when the patch, that is due to southward transition of the interplanetary magnetic field, you can see that the jump in the convection from 100 meters per second to all the way to more than 1 kilometer per second during that time. And that there is a lot of variability in that convection, but the convection remained more or less high during that period. So that is the type of structure we are talking about. And for this particular study, I'm going to use 6 GNNS, or receivers of the Canadian High Arctic Ionospheric Network. And we use 4 ionosones distributed in the polar region. And we also use Lyatskaya imager at Resolute Bay, and then solar wind monitors the L1 first Lagrangian point. That gives us the contextual of the interplanetary medium. So these are the stations I'm looking at. On the right-hand side, those are the locations of the GNNS receivers, or the IPPs. And the left is the map showing the Resolute Bay 630 nanometer image. Within that, you have the stations we are talking about. So we are, in a way, covering a broad region of the polar region. So as I said before, the contextual information of the solar wind IMF conditions. So you can see the BY, the east-west component of the interplanetary magnetic field. Predominantly in the initial period, it was positive and then turned negative. But the important thing note here is the BZ, that is the primary component of the convection variation in the polar wind or polar region, also controls the energy input into the system. So initially it was northward, but you can see at a sudden transition, southward transition around 4:15 UT. And that was a quick transition and then remained southward during for an hour and a half, eventually turning northward. And so, but this is the time period I'm talking about. You have energy input in the system through this, the southward turning of the IMF. Yes, question. I see her.
It's not a question. I just wanted to remind you that you have 2 more minutes left.
Okay. Okay. So that's the condition. So if I'm not going to play that. So when we look at the TC variation across the ray path, you can see the signature of the patch all the way from Eureka to Hall Beach in lower latitude, and that is shown in the right-hand side. And if you look at Ionosonde also, you can see the structure of the patch or patch signature in that. So that measures the convection. And this is again another way to look at the patch. And this is the convection during that time, high convection. And this is the convection measured using the airglow technique, using the full correlation analysis. They more or less agree. So the point I'm trying to make here, this is the point. So if you consider purely no production ionosphere, and so that is the recombination expression I'm going to use, and then apply the continuity equation, and then assume that no production, as I said, and then F region is purely made of O+, then we can do a back of the envelope calculation of what is the expected electron density purely by the transport and chemistry. So here, for that particular patch, that is the average TEC enhancement associated with the patch as they move from near the origin to lower the latitude. You can see that amplitude of the enhancement of the TEC decreases as it moves along. On the bottom, that is the interesting part. So that is the measured peak electron density at the 4 Ionosonde locations. And by the simple model described in the previous slide, I was able to calculate what is the expected electron density for that particular event, and that red dots are the expected electron density for that. So in a way, they are not one-to-one, but the trend is similar by just applying a rudimentary chemistry model. So in a sense, it is telling that as the patch converges across the polar cap, the chemistry, it decays at the chemical time scales. So that is my summary. So chemistry is the factor in this case that controls the decay of the patch.
Hi, Chandran, did you finish? Thank you for your presentation. Let's see, we have any questions?
I have one.
Can I ask? Okay, go ahead.
Go Shri.
Okay, so I have a question for Dr. Jayachandran. So you have shown the calculated and measured fluxes, right? So there is
electron density.
Yeah, electron density, sorry. So there's about an order of magnitude difference in the both. So what could be the reason? Because in your model, you have included both transport and chemistry, right? So what other factors might be contributing to that difference? Like what else
because
you have
I didn't include the time history, right? So I didn't take into the time history. So any patch that moves has a history with it. So it started with certain electron density initially, right? From wherever they form, but I'm not tracking it when the time it forms. I'm tracking it when it got to Eureka, right? So I didn't take into account what is the initial electron density.
Okay, so the initial density. Okay.
Yeah, that is one of the maybe one of the reasons, because I don't know the time history.
I had the exact same question, Shri. Thank you, Dave.
Okay.
Okay, thank you.
Thank
you, Tahil. Now, the next speaker is not here. I think we can go ahead with Ryan Imam, that we will speak about machine learning for curing scintillation data in Sanai for Antarctic Station.
Emilia, I see, no, Emilia, sorry, I see in the attendees Tamara Yegorova.
Yes?
In the list of attendees, I see Tamara Yegorova. Allow to talk.
Okay.
Okay, Tamara, I allow you to talk.
She's here? It's not here. It's not in the list.
Yes, she's in the
Okay, I
attendees list.
promoted her as panelist. Tamara, could you?
Yes.
Share your screen, please.
Tamara?
It's here now. Okay.
Okay.
Well, then, sorry. Tamara Yegorova will give the presentation now then. Magnetic field mapping of the Argentine Islands shelf zone west of the Antarctica Peninsula. Are you there, Tamara? Tamara?
IT team, can you help us?
What?
Oh, Tamara,
Okay.
Tamara.
Yeah,
Tamara.
yeah, ты включила.
Yes,
Okay,
I
I'm
follow
here.
you. Try to share your screen.
Okay, I try. I
Okay,
try.
you should be
I
able.
try. Надо загрузить это самое share screen. So, and how to share screen? Нет, оно у меня там. Оно у меня там, смотри. Давай. Я не знаю, где она, куда она делась. Just a moment.
Scar IT team, can you put all the attendees in the panel list, please?
I asked, but it seems that
Okay, and you know, 2 days ago, I sent my presentation to organizers. Maybe you have it at yourself.
no, we do not have, Tamara. I'm sorry, but
Yeah,
are you
I
able to
understand.
share the screen?
I cannot share the screen. I cannot see it. Где она?
At the bottom, middle, the green.
Это было, я видела. Just a moment. Oh, share screen. Just a moment.
Okay, you found it.
Okay.
Yeah. Оно, может быть, show all options. Нажми просто на него share screen. Я не знаю.
Tamara, if you can send us, me or Emilia Correia, your PDF, your PPT now, so we can go ahead with your.
Okay, please.
So maybe, Emilia, could you invite Ryan Imam to talk? In the same time, Tamara will send you.
Okay.
The presentation.
Да, okay. Please.
Yes, so please, Ryan, Could you share your screen, Ryan? Here we talk about, as Emilia said, the machine learning for curing simulation data in Sanae for Antarctic Station. Okay.
Can you hear me?
Yes, and we see also the presentation. Okay.
Okay, thank you, Giorgiana and Emilia. Hello, everyone. My name is Renata, and I'm a research fellow at the National Institute of Geophysics and Volcanology in Rome. And I will be talking about our work on machine learning for curing scintillation data in Sanae Antarctic Station. And I will start immediately by explaining the position of this particular station, because this station is, there is a receiver, a scintillation receiver, that is interested in monitoring the ionosphere when the ionosphere is in disturbed conditions of scintillation. And in particular, the position of this station does not allow the station to always monitor scintillation, because it's sometimes outside of the vision of the station. So sometimes it's not able to see the disturbances. And in this figure, if you look at the two black circles, the area between those circles, so it's like a ring, is where usually scintillation happens, even in normal days when the sun is quiet. And when the sun is in particular active, we see the area, the ring between the two red lines, usually are disturbed. So the station, which is the black dot, and the vision of the station, which is the dotted circle, sometimes is in and outside of this interested region. And this circle in particular is at the elevation mask of 10 degrees, which basically means we are looking at all the sky. And if we look at the GNSS measurements, in particular in this figure, for example, the GPS measurements, we see that the measurements, which in this figure are 24 hours of measurements. So these are all the GPS measurements recorded by this station for 24 hours. We see that the portion of the sky on the bottom southeast is in particular scarce. There are not many measurements. And if we look at the figure on the right, which is the area that usually have an interesting set of measurements, we see that, okay, we don't see a lot of scintillation data, which means that our data is really, really scarce and valuable. So we don't want to mess the data or to discard a lot of data. But the truth is we cannot set the elevation angle to very low degree because of basically the propagation environment of the signal from the satellite to the receiver affect the signal in this region. And basically what we usually do is we discard all the measurements that are below 30 degrees. And if we look at the dotted circle now, we don't see much of the interesting measurements anymore. And in GPS measurements, let's say we basically don't see much anymore. So is there any way to, let's say, increase the amount of measurements that we can see by lowering the elevation mask without including the measurements that are contaminating the data? And this is what we are trying to do, but we remember that multipass, which is what is happening because of the environment around the receiver from lakes, buildings, is not the only contamination of the data. We have much more. We have radio frequency interference. We have also the errors from the satellite, from the receiver itself. So it's a lot of contaminations, and we have scarce data. And if we put above all of that, we have by now more than 6 years of continuous data collection. So that's second by second, minute by minute, you get measurements from this station, and that's a lot of data, which means it's not feasible anymore to try to detect these small anomalies by, let's say, human operators. And what happens is We usually implement detection mechanisms that are based on thresholds. What we are trying to do in this period is to implement machine learning models. So we want to detect scintillation, we want to identify these contaminations and put them out of our measurements using machine learning techniques. And if I want to talk about machine learning in one slide, only one slide, basically what we do is we have a phase that is called training phase, where we bring machine learning model, which we don't know which one is good. So we bring a lot of machine learning algorithms. We put them here and we try to train each one of them to understand what is scintillation, for example, in this case, and what is not scintillation. And the output of this training phase is a model, a data-driven model that we take and we use in our application. And this is basically what we are doing here. And the first question we have is which of the measurements that the receiver gives us we are going to use here. And so we start by the easy solution. We take all the scintillation data from the receiver and we group them in blocks of 3 minutes. We choose 3 minutes blocks because this has been working for us for some applications. And we start from there. So we have all data from the Genesis ionospheric monitoring receiver prepared in 3 minutes blocks. And we bring a lot of machine learning algorithms. In this case, exactly, we have 70 models, and we train them one by one, one by one. And in this figure, the x-axis is the models, the 70 models I mentioned. The left blue is the accuracy of the model, and the right, the left, the Y, the red is basically the misdetection and false scintillation alarm. And these are two important metrics because we want to know when we are getting alarm for scintillation when there is no scintillation, and the opposite when scintillation happens, but we misdetect it. And if we look in particular, what happened is that most of the models report that they have very good accuracy in training and testing phases, but some of them report very low scintillation, misdetection, and false alarm. And these are the models that we want. In particular, if we look at the model with the green dashed line, this is the bagged T model, bagged tree model. And this model basically reported that it was able to learn how to identify scintillation and with a very good accuracy. And actually, we have tested this model with data that include both scintillation and multipass. So that's usually what causes false alarms. And here it says it's able to work. But then the next question is, which of all these 23 measurements that we take from the receiver were useful, for example, for this model? And so we took the first assumption, maybe these are the scintillation indexes. So it's for sigma phi and all the scintillation related indexes. And in the previous slides, we noticed it's around 95 accuracy and 5% on the red lines. This model, the accuracy now is lower, it's only 90, and we report a lot of misdetection and false alarms, which means actually the scintillation indexes are not what exactly makes this model work perfectly. We have been searching around the features, of course, systematically, and we found that actually these features are the ones that give us the good accuracy. If we take only the TC measurements, we take out all the other measurements, so only 3 measurements grouped in blocks of 3, we find that we are able to get a model that reports very high accuracy and very low scintillation misdetection and scintillation false alarms. And this is basically the work we have been doing. We started with including only multipath, and the ideal solution will should also be able to distinguish the other contaminations, so identify scintillation even in case of there is, for example, radio frequency interference and this stuff. So this is what we have been doing so far. In a summary, we applied machine learning techniques on the septentrion receiver data to detect scintillation. So the septentrion receiver in Sinai. And the models take as input all the ionospheric measurements provided by the receiver, including the scintillation metrics, and it decides if scintillation occurred based on a wide set of scintillation measurements. And we investigate the usefulness of each measurement for detected scintillation by analyzing how much the model relies on the measurements for identifying scintillation. And the decision mechanism is a data-driven model that can be used to curate the repository of synthetic data before incorporating the synthetic data in further studies. So this is the objective. So far, the model is able to detect scintillation in presence of multipaths. And the next step is to gradually include the other impairments, associated anomalies, radio frequency interference, and so on. And thank you for your attention.
Thank you, Ryan. Thank you for a good
you,
presentation. We have only one question from Pierre Cilliers. He asked about how frequently do you see RF interference in the scintillation data from sonar?
Okay, I have been detecting signatures that look like RFI, but I'm not sure which kind of RFI interference, because it's not always the harmful interference. So sometimes it's just the instruments around the receiver. They have sometimes, let's say, oscillations or high frequency oscillations around the measurements. So it happens, yes. I'm not saying harmful, intentional, but there's always some interference.
Thank you.
Yeah, I think it's okay.
Emilia,
Thank you very much.
Emilia, can I say something to all the attendees and panelists?
Yes.
Please check when the invitation to become panelists arrive, you have to accept. Otherwise, attendee speakers cannot share the screen. So please look at the invitation when arrive. You say you have to reply yes. Okay. So Tamara, are you? I invited you a lot of time to become panelist. Did you move? Did you accept?
Okay. Oh, I'm here.
Okay.
One minute.
Okay.
Hi. Okay.
Just a moment.
Finally, please.
Please, Tamara, could you start your presentation about magnetic field mapping of the Argentine island shelf zone west of the Antarctic Peninsula? Go ahead.
Tamara, you have your microphone closed. You are mute.
Okay.
Okay.
Hello. Hello. Could you hear me?
We see and listen you, but please share your screen.
Okay.
Because now you are habilitated.
So I sent my presentation to you by email.
To you who? To me or Emilia?
To you, Giorgiana. Yeah, yeah.
Okay. So I'm going to see.
Yeah, please.
Oh, yes, I see. So now I'll try to share. Okay. Should be this one. Can you see?
Yeah, I see.
Okay, please let me say when I have to go ahead.
Okay. Okay, so my topic deals with magnetic field mapping on the part of Antarctic Peninsula at the location of Ukrainian Antarctic Station, Academician Vernadsky. Just next slide, please.
Sorry, I have to, sorry.
Make it full screen.
No, because I have to, okay.
Just to save it, I think.
Yes.
Okay. The EDMAP project, Antarctic Digital Magnetic Anomaly Project, is one of the main projects in Antarctica. And due to its activities, the magnetic map of Antarctica was constructed based on ground, marine, satellite, and aeromagnetic service. And so an important input to this research are contributions from local studies and local magnetic service, you know, which was done, which was done by over certain areas by different countries and organizations. And so I just show you, this is red star, show the location of Ukrainian Antarctic station, just here. And a spectacular feature of the Antarctic Peninsula is a strong form arc. So you can see it's here and always here. So that is a magnetic anomaly of Antarctic batholith, which marks the magmatic arc of subduction-related origin due to subduction of and accretion of some domains to the Gondwana, Western Gondwana margin. And so, please, next slide, if it's possible. Okay, so this is the Antarctic Peninsula batholith magmatic anomaly. So you can see in more detail here. And it's assumed that this composed of a number of terrains, from 2 to 3 terrains that we accreted together during the Mesozoic, Cenozoic subduction to the Gondwana margin. Next, please. Next slide, please. Okay, and you know probably that the Antarctic Peninsula is the most studied area by deep seismic studies. So that is the seismic studies, seismic survey with explosions to study the crustal structure of the Antarctic Peninsula. And so totally it was conducted 20 profiles. And along the longest profile, it was possible to obtain a structure at the transition from thin oceanic crust. This is a top cross section beneath the thick continental crust of the Antarctic Peninsula, and the lower section shows the structure of the continental crust just at the location, near the location of Antarctic station, our Antarctic station. So that is typical continental crust we see. And this profile, lower profile, we used for construction the magnetic model on the longest profile. Next slide, please.
Okay.
Okay. Next slide.
Sorry, this one, it's okay?
It's okay. Yeah, next slide, please, if possible. Please help me.
This one.
Next.
There is a lag, Giorgiana, I think.
Yeah. The screen is hanging.
Yeah. No.
One.
No,
it's
no.
it's
Before that.
Oh, okay.
Okay. This one.
Okay, this one.
Oh, this one. Yeah. Okay. And so, and I can show here the magnetic model using that seismic model as a constraint, and we see that this magnetic anomaly, huge magnetic anomaly of Antarctic batholith, is caused by plutons in the crust of mafic composition. Next slide, please. Next. Okay, biochronology. Now, before that, this one, yeah. And this slide shows that the composition of the rocks of the Antarctic batholith, that it was formed during four stages of magmatic activity during the Permian-Triassic times. And in our region, we have only these youngest two events which characterize the granitic, granodioritic, and gabbroid intrusions. So next slide, please. Okay, so this geological map and stratigraphic map and stratigraphic scheme shows that we have know from geology. Our knowledge on geology comes from just outcrops on the Iceland, it's just here. And it shows, and in this area, we have the oldest rocks, sedimentary and meta-sedimentary rocks of Permian-Triassic. And so Jurassic Cretaceous rocks, this is volcanic rocks, and also in this green, red and yellow are rocks that forms the Antarctic batholiths, from mafic rocks to granodiorites and granites. And so this all these three groups are good seen in the geochemical diagram, which shows by green gabbroids and yellow one granodiorites, and red one area, this is granites. Please, next slide. So you can see these rocks that exposed on the islands and on the margin of the Antarctic Peninsula. So that is gabbro rocks of and dikes in gabbro. Next slide. And also this is volcanic rocks. You can see here that is a Jurassic and granites. So that is granite. So that we have, what I can say, that we have great diversity of rocks in this region. Please, next slide. Okay, this one. So here I just cambio. So that is before.
Tamara, you have 5 minutes. Okay.
Okay, I try. And okay, so just I try to say about the magnetic survey. And so this is just show this small area. It just show our area of magnetic survey, which was conducted using these bolts. This is the bolts, zodiac bolts, and using the proton magnetometer. And also all these rocks that I show, that I was said about, they are differ by their magnetic properties and physical properties, especially magnetic properties. So next slide, please. Next one. Okay. And that is the, so next slide, please. Next one. Next one. Next. Okay, this one. And so that is the area of our magnetic survey. So left one can show us the scheme of tracks of the magnetic survey, which was conducted during 8 field seasons and resulting in construction of this magnetic map on the right. So we can see 2 stripes, one stripe of negative field, that is the blue one, and large areas of positive magnetic field, the pink and red one. So we interpret them as caused by different composition rocks, by rocks of different composition. Next one. So, and this map shows the long wavelength components and short wavelength component from our initial resulting magnetic map. Next one. Also, we constructed a two-dimensional model, a cross-section of our magnetic model, and to study the crustal structure of the upper crust and the shape of magnetic bodies and their magnetic properties. And we can see that majority all the magnetic bodies are located down to the depth of 20 kilometers. And their magnetic susceptibilities indicate that these magnetic highs are caused by bodies of gabbro rocks. So these parameters are in the table. Next one, please. And also now we comes to the interpretation of this magnetic map. So what we have? We have magnetic map. We have composition and type of rocks exposed on the islands, on small islands, and that they differ by their, and we know, and we try to interpret our magnetic map in sense of the composition of rocks and tectonics. First of all, it was possible to draw faults. You can see these right lines, dashed red lines. So that is the main fault of northeast orientation, and four faults across it. So that is a system of suborthogonal faults in our area. Please, next one. Next one. Okay, and this orientation of these faults is in correspondence with the geology. This is with the geology map, because the same faults they were detected, and with the bathymetry map. So it's in good correspondence with the data. Okay, next one.
1 minute, Tamara. Okay.
Yeah, okay. And so I can show you our geological construction. Next one. Okay. Okay, good one. So on the left, you see our magnetic map, and to the right, our geology map that was constructed on interpretation of this magnetic map using the rocks exposed on the islands and their magnetic properties. You can see that the blue color indicates the all the volcanic rocks, and blue one and red one that is the granites of Antarctic Peninsula batholith with the bodies of gabbro rocks by green one. You can see. And so next one, just a moment. Okay, one more. Okay, and so you can compare our map that we get as a result of our magnetic survey and its interpretation, And the map and our knowledge that we knew before, just very exposures on the islands. Okay, so that is next one, and that is conclusion. If I have no time, that is the result. Okay. Thanks for your attention. And,
thank you for your presentation.
Sorry for troubles.
Okay,
Tamara, I suppose
much.
that your kind of investigation are really interesting. Also to say to all the attendees and panelists that the very last time we combine two different sessions. One is the brackets, the great session, and the other one is the session devoted to magnetic magnetic activity. So this is why sometimes we see something that is not exactly included in the grape story. Please.
I would like to have a question to make the link between grape and what Tamara just presented there. So during campaigns, you measure the magnetic field on a boat, I think, if I understood well, to retrieve the crystal anomalies. How do you correct from the main geomagnetic field? Because in this region, the magnetic field is really strong and also really active. So how do you remove the main contribution of the magnetic field to retrieve the crystal magnetic field?
What crystal you mean?
From the rocks.
No, sorry. I have no any idea on this.
Okay, because you don't measure the...
Maybe, Nicolas, we can continue. We know we have the email by Tamara.
Please, could you write me a question, your question? Okay.
Thank you very much.
Thank you.
So, Emilia, please.
One more time. Okay. Thank you, Tamara, one more time.
Yeah, thank you. Thank you too.
Okay. Thank you. We will go to the next presentation by Giorgiana Pandey that will present the polar dissemination of the ionospheric disturbances associated with the 2022 Tonga volcanic eruption.
Hello all. Yeah. I'm
Okay.
sharing my presentation. Is it visible?
Not yet. Okay. Excellent.
Just put in full yes.
Okay, so greetings to all and thanks very much for the opportunity. I'm going to talk about the propagation of ionospheric disturbances and the atmospheric pressure waves associated with the Tonga volcanic eruption in Arctic and Antarctic regions. So as we know that...
I think it's not in presentation mode because it stopped in the first slide and it's not full scale.
No.
Screen.
From my side, it's full screen.
But not here. Try again.
Okay. Is it okay?
Not yet.
Emilia, I suggest to go ahead also because it seems to me that we are able to see in any case. It is not in presentation, but please go ahead.
Okay, try to change the slide if it's working.
It's working or not?
No. Is yet in the first slide.
So that's the way you share the screen. You need to share the presentation screen first and then put it in the presentation mode.
That's what I did. It is coming in not slide mode.
Okay.
Change to the
Please
second slide if it's working. If it's working, go ahead.
Okay, so I'm talking about the volcanic Tonga volcanic activity which erupted on the 15th January, as we all aware, 2022, in the Honga Tonga Island. It is a submarine volcano, and it triggered the large atmospheric shock waves. As we know that during the volcanoes of submarine volcanoes, they erupt in two ways, either a divergent plate boundaries or one is subduction. And this volcanic eruption is the subduction zone volcanic eruption, and it's the signature of this volcanic eruption recorded throughout the globe in the earth as ionosphere. So what I did here, that we have a Indian base station in Antarctica, which is called as Maitreyi. I have analyzed the 3 days data. One is the event day, and after the event day, two more days. What we can see here, the black lines are showing the atmospheric pressure, which we can see here from here, a clear indication how the.
To interrupt, but your slide is not moving. I mean, it's still on the first page.
It's not moving.
Yeah, now it's
moving.
Try once again.
Okay, now we are in the second, the third.
Yeah.
Now, in the third slide.
Yes, now you can.
We are in it's okay? Slide.
Yeah, it's okay.
Okay, so please check when you change the slide.
It's showing on full screen mode or not?
This is the number 3, propagation of the geospace.
Yeah.
Okay, please go ahead.
So here, what we have analyzed is the ionospheric DEC, which is derived from GPS. We have a Indian base station, which is called Maitreyi. I have analyzed 3J data for event day and after the event day. So from here, we can see that the black lines, which are the atmospheric pressure waves, it's showing a clear signature of the arrival of the Tonga volcanic eruption. Associated, we have the colored lines which are showing the different satellites derived TCs, and we can see on the event day both are the coinciding with each other. Atmospheric pressure is we see as the early signature, then the ionosphere, and other two days we are not seeing any significant signatures. Also, I have taken a GPS station in Greenland, that is Arctic THU2, and this Arctic station is also showing the pressure anomaly. It's clear, we can see on this between the 15-30 hours time frame. And here also I analyzed 3J data, and we can see the ionospheric and the atmospheric pressure waves, both are the coinciding. From here, this is the map, shows the how I have taken for the detailed analysis. I have taken the 4 sites in the Antarctic and the 4 sites in the Arctic region, and try to analyze the how the wave propagation reaches towards the Arctic and Antarctic regions. Slides are not coming.
You have to move on to the 4th slide, no?
Yeah.
We're talking about the 4th slide, right?
It's right or not?
Okay, now continue.
So I already discussed about that. I have taken a GNSS site that is located in Greenland, Arctic, that is THU2, and we can see from that figure that on the event day we have the surface pressure anomaly around the 15-30 hours, and other two days not much significant anomaly, because located around the 12,000 kilometers from the Tonga volcanic eruptions. In next slide, is it changing?
Yes.
In next slide, I tried to know how the waves are propagated towards the Arctic and Antarctic, both the polar regions. We can see from the figure I have taken the four sites in the Arctic region and the 4 sites in the Antarctic region, starting from the low latitude towards polar regions. And from figure, we can see that the Lamb wave, which have approximately 300 meters per second, traveled towards the Antarctic regions and Arctic also. In next slide, I will show the disturbances from the Tonga traveled along the Great Circle in both the directions. We are in the study of for the Great Circle along the globe, how the disturbances change and how the pressure spectrum occurs due to this volcanic eruption. We are in the mid of that study. So this is the Antarctic region, how the waves travel. We have we can see the 2 velocities. First one is the Lamb wave, which is the 300 meters per second, and another wave we have observed in the Antarctic region is the 360 meters per second wave. Like the Arctic, Antarctic also follows 2 paths to reach to Tonga. One is the direct and the other is the indirect. The amplitude, what we can see is the amplitude of the filtered TEC in the Arctic is less than that in the Antarctic. Disturbances in the ionosphere in Arctic region reaches bit late from the Antarctic. So from the study, we can conclude that the polar regions, the Arctic and Antarctic, recorded the effects of major undersea volcanic eruption that occurred 15 January. Maitri, the Indian base station in Antarctica, located around 9,784 kilometers from the epicenter, has also recorded a leap in atmospheric pressure accompanied by the ionospheric disturbances. A similar jump we can see in Arctic region also, which is more farther than the Antarctic. And in the Arctic region, the ionospheric disturbances travel at a speed 360 meters per second and 300 meters per second. And in Antarctic, we see only one wave, that is long wave, which has the velocity of 300 meters per second and very feeble and sustained for the lesser time. Thank you very much.
Thank you, Jendra Pandey. Any questions? No.
I have a question.
Yes,
okay,
please.
go ahead.
Okay, so you are talking about the TEC disturbances at Maitri during the Tonga eruption, which occurred on 15 January, right?
Yeah.
So if I see in your figure, the TEC disturbances, like it's not like more than 1 TEC unit or something.
Because I used filtered data here, not the raw data we observed from the GNSS TEC. I used a Butterworth filter, and because the magnetic anomalies and magnetic field is very strong in Antarctic as well as in our polar regions. So I use the filtered data to analyze the TEC.
But usually the TEC in Maitri and all, it's not very smooth. It's if you see the diurnal variation, it's very fluctuating.
Yeah.
So if you compare it with the pressure and the fluctuations, if it is like in the difference of 1 or 2 TEC unit, it could be because of other factors also. It's like a very common feature for the total electron content in the
I can understand, but the thing is, we have an atmospheric pressure signature at Maitri station, so it's a better understanding that we have the atmospheric anomaly, so we can correlate with that ionosphere. And we are taking the different satellite measurements, around 32 satellites we observed, and we see not much disturbances. 2 or 3 satellites are showing that significant amount. which I have shown here.
I think if it is not like a more than like
Shreedevi,
26
can I
unit,
stop
I think you should
please, because we
probably.
are 5 minutes in late. You can
Okay.
continue
Yeah.
probably in
Okay.
the
In the
separate
chat,
chat
yes.
or via email. Thank you. Thank you
Okay.
once
Thank you.
more.
Okay.
Thank you
Okay,
one more. Let's start with presentations. Now we have Junjun Liu that will present simultaneous ground-based optical and superdarn observations of the interplanetary shock sudden compression. Please, are you there?
Sorry,
Okay,
just a moment.
go ahead.
Okay. Oh. Oh. Yeah, sorry. Okay, could you see the shared presentation?
Yes, can you go full
Yes.
screen?
Okay.
Okay, thank you very much. Hello, everyone. My name is Jinjun Liu from Polar Research Institute of China in Shanghai. Today, I would talk about some auroral and ionospheric convection plasma observations in the Chinese Antarctic and Arctic observatories. We know the when the solar wind disturbance interacts with the Earth's magnetosphere and ionosphere, it triggers large-scale optical auroral signatures, including the polar light brightens in the day-side cusp region and then propagate along the dusk side and the dawn side to the night side ionosphere, and simultaneously the ionospheric plasma convection responses instantly. For example, enhanced convection strength in the day-side ionosphere and appeared intense sunward convection fluxes and including prompt and complicated flow reversals just after the interplanetary shock or sudden enhanced solar wind dynamic pressure arrival to the Earth's space. Here, I want to show the, this is the solar wind interacts with the Earth magnetosphere, and we use the Antarctic Zone Sun Station and Arctic Yellow River Station locates in the Svalbard Nordosum community. This both observatories locates in the higher latitude, exactly around the cusp regions, so which could measure the direct solar wind and magnetosphere interaction phenomena such as the polar light auroral brightening and plasma convection and TEC responses. Here, I just want to show when the Yellow River Station locates around magnetic norm, exactly around 12 magnetic local time, which the Yellow River Station was covered by the Superdome radar locates in Finland, north of Finland. So both of Superdome radars and all sky imagers could supply the direct responses, direct magnetosphere response to the solar wind disturbances. Here we show the solar wind dynamic pressure enhancement and the interplanetary magnetic field disturbance. The disturbance propagates to Earth's magnetosphere after 42 minutes. So we can see the sudden enhanced geomagnetic index. This solar wind dynamic, solar wind disturbance triggers the typical sudden impulse, which was measured by the geomagnetic flux gate magnetometers locates from the high latitude to equatorial region. And this is the auroral observations in Yellow River Station. We can see before the interplanetary shock arrival to the Earth space, the auroral signatures was relatively quiet, especially for the diffuse aurora locates in the lower latitude in the equatorial region of the all-sky camera. The diffuse aurora was quiet, but just after the solar wind disturbance arrived to the Earth space, the diffuse aurora in equatorial region brightens suddenly and propagate to higher latitude. And this phenomenon is quite instant and prompt. And simultaneously, the discrete aurora, which was captured by the 630 nanometer all-sky images, the discrete aurora responds to the interplanetary shock gradually, and such kind of discrete aurora just propagate to lower latitude region. We can see the shock movie depicting the diffuse aurora in equatorial region response to the interplanetary shock instantly. Here is the discrete aurora in high latitude region, which shows the gradual equatorial movement. This is the kilogram to show the diffuse and discrete aurora response to the solar wind disturbance. We can see clearly the diffuse aurora response to the shock wave instantly. And this is the super-long radar observations from the top to bottom. This is the power spectrum, and this is the velocity, and this is the spectral width. We can see just after the shock arrival to the Earth space, there are reversed convection flows in the high latitude region, and this is the common plasma flow anti-summer in polar cap region. Here we show the large-scale plasma convection measured by the super-long radars. We can show the four-cell convection patterns. This is the typical convection map driven by the lobe reconnection in the high latitude magnetopoles. Here we show event study in personal sector. In this event, the Antarctic Zhongshan station locates in the dusk side, while the Zhongshan was covered by the Siwa East radar locates in the Siwa station, and simultaneously the South Pole station around the local node has good optical auroral observations. This figure shows the solar wind disturbance, which propagates to the Earth space around 50 minutes. And the interesting is the auroral observations around in the Zhongshan station just show that before the shock arrival to Earth space, there was discrete aurora in high latitude region, but just after the shock compressed the magnetosphere, the aurora intensity decreased for about 3 minutes. And then the interesting is the aurora intensity in South Pole station. The aurora intensity increased suddenly, and this increasing lasts about 3 to 4 minutes, which is opposite to the observational results in the with the Zhongshan station. This is very interesting, and simultaneously the ionospheric plasma convection measured by the superdome radars over Zhongshan Station shows the plasma flow. This is the greenish shows the plasma towards the radar, namely sunward plasma flow. This is the pink, the yellow dots shows the plasma flow reversed from sunward to anti-sunward, and simultaneously the auroral optical auroral intensity diminished. This is a comparison between optical auroral superdome radar and flux gate magnetometer flux gate observations. This is an event showing when the solar wind disturbance interacts with the Earth's magnetosphere film. The phenolite current formed in the polar ionosphere and the way which flow into the polar ionosphere in the dusk side, and flow out of the polar ionosphere in the dawn side, so which corresponds to the auroral decrease in the dusk side and auroral increase in dawn side, which is this observation is a very good observational evidence for sudden impulse physical model. That's all. My discussion. My conclusion is the shock triggered enhanced wave particle interaction, which responds for the intensified diffusor. This phenomenon was captured by the Yellow River Station in Svalbard, and enhanced highlight to reconnection rate by the solar wind disturbance has close relationship with the local known discrete auroral enhancement. Both phenolite current system and phenolite resonance activity associated with the sudden impulse or sudden commencement contribute to the personal auroral evolution and ionospheric convection flow reversal. Thank you very much. 谢谢.
Thank you, Junjun. We have one question in the chat. Shiprashinha wants to know if the particles came from the inner magnetosphere. Do you know from where these particles come?
Okay. Thank you very much. The precipitating. Yeah. I mean, my discussion was the solar wind disturbance interacts with the Earth space. The plasma wave intensity increased, and the wave particle interaction correspondingly increased. So such kind of plasma process leads to the more particle precipitated into the polar ionosphere that triggers the shock aurora.
Emilia, there is one more questions, but because we are okay.
Maybe you can answer in the chat, John.
Yes.
Maybe you can answer in the chat.
Okay.
Yes,
Thank you.
please, because we are late. So sorry.
Thank you one more time. Yes.
So,
could you close your sharing?
Change.
Okay.
Via chat. Thank you again. Thank you once more.
Thank you. And
Thank you very
we
much.
go ahead for the last speaker, Andriy Zayusovsky, that will present first results of RF measurements on board of the Ukrainian research vessel Ionosphera on the way to Antarctica Peninsula. Are you there, Andriy? Okay.
Do you hear me?
Yes.
Can you see my?
Go ahead.
Andriy, we can see your presentation, but we cannot listen you. Please try to talk.
Do you hear me now?
Yes, please.
Okay. Okay. Good night. Good
You have
morning.
10
Good
minutes,
day.
Andrei.
Yes, I'll try. And good evening. We are from Ukraine, and I will tell you about the first results which we obtained during the first voyage of the Ukrainian research vessel ionospheric to Antarctica. So last 30 years, that was flagship of British Science Navy JCR, James Clark Ross. I'm sure that everybody know this ship. A year ago, Ukraine was bought this ship and renamed to the ionosphere. Last October, she came to Odessa, and we started to prepare to the first trip of our ship to Antarctica. We equipped ionosphere with antenna. This is blue one. It is almost horizontal dipole, which we use for the receiving side of our ionosomes that work at the Ukraine and Vernadsky station in Antarctic Peninsula. We used another pair of HF antennas, which worked with two-channel Doppler receiver, and we erected their VLF antenna, with two perpendicular frames and pin antenna. So all these antennas was hung at the fine direction deck at the upper side of the ship. And during this voyage that continued less than 3 months, but more than 80 days, we solved 3 different tasks in HF frequency band. So we carried out 2 position synchronous sounding of the ionosphere using the signals of ionosomes located in Ukraine and at Vernadsky station. So we have simultaneous vertical and oblique ionograms. We carried out the static sounding of the ionosphere using the signals of time series stations and spatial transmitters. And this is observation carried out synchronously with the receiver at the Vernadsky station as well. Radioceanographic sounding. So we use the signal from Vernadsky, and we use skywave for estimated scattering from the ocean surface waves, and to solve the reverse problem for estimating the parameters of the ocean waves. And in very low frequency band, that was monitoring of planet activity and using the tweak atmospherics for some measurements of the height of D layer of the ionosphere. Okay, and start from the long distance propagation. So we have pair of receivers at Vernadsky, and we use the transmission from RWM and CHU station. And this experiment we conducted more than 11 years already. And we have a new pair of the same receiver. This is based on radio technology on board the ionosphere. The ionosphere started from Odessa port on 28 January, and we was lucky. And you can see the point where ionosphere was on 24th February when war started, and because ionosphere was near the equator, so Russianism did not kill ionosphere yet. And this type of observation could be used for estimating the spatial correlation between the signals received at the Antarctic Peninsula and on board the ionosphere. At this slide, you can see an example of the daily spectrograms of RWM signal and CHU signal observed at the ionosphere that located at the time in the Drake Passage close to the Vernadsky and at the Vernadsky. And one can see that the spectrograms are similar, but some differences observed between the signals, and that would be used in the near future to estimate the spatial correlation of the fields far from the transmitters. So the distance between RWM and Vernadsky is approximately 16,000 kilometers and 12,000 between CHU and Vernadsky. So next, radio oceanographic observation. So sometimes, not every day, but sometimes we observe the scattering from the ocean sea waves using the antenna on board the ionosphere. At this slide, you can see example for the 17 April, when ionosphere was on the way back from Vernadsky to the South America. And this is scattering from the ocean, and you can see so simple model. So usually this problem solved in one position radar or two position radar, but usually for the stable receiver and transmitter, we try to solve this problem for the moving ship, and it is very possible as for our opinion. So you can see one more example of the spectrum with scattering from the ocean surface that was on the way to ionosphere to the Antarctic Peninsula. And it is possible to use the spectrum features to estimate the elevation of the sky wave. So you can see the simple modeling of the spectrum for the different elevation angle. And so the asymmetry of the spectrum is very difficult for different elevation. And it is possible actually to use the ocean waves as an additional antenna for this task. And about ionospheric sounding. So we developed and manufactured in cooperation with ICTP and with New Brunswick University portable Doppler ionozones. One ionozone that we're working in Kharkiv region now, and it is not occupied. We control this ionozone. And we installed the receiving site on board the ionosphere. And so when the ship was on the way from Odessa up to the Greece shore, we received the signal from the Ukraine, and we have pairs of vertical and oblique ionogram. And when ionosphere was in the vicinity of Vernadsky, we have one more pairs of oblique and vertical ionograms. At this slide, you can see one more pair. So at the left panels, comparison of vertical ionogram for Ukraine and oblique ionogram on board the ionosphere when she was at the Black Sea, and vertical and oblique ionogram when ionosphere was in the vicinity of Antarctic Peninsula. And about VLF observation, so we determined the location of source of light and activity. And when this source lived so long time, we estimate the variation of virtual reflecting height of the signal in a very low frequency band. And so this is only preliminary results. Now actually we process this data, and we hope we obtain more information, more results. My concluding remark. So we carried out the first measuring campaign. This campaign was conducted during almost 3 months. We work in high frequency band and very low frequency band, 5 different scientific fields. And we would like to invite our colleagues to take part in future voyages of Ukrainian research vessel ionosphere. You can see coordinates of our director, Dr. Evgeny Dikey, and science deputy director. And if you would like to take part in further expedition, please contact with them. So now ionosphere is in Cape Town. Unfortunately, she cannot return to Odessa, but this vicinity in Antarctica, and we need to support of our colleagues. And please support us by participating in the future voyages on board ionosphere. Thank you very much for your attention.
Okay, Andrew, thank you very much. We have no time for question now. If there is any question, please put in the chat and Andrew will answer you, okay? Thank you everybody to participate in this section, in this block. And we invite you to continue online because the next block will start in 15 minutes, okay? And please see the poster section of our session. We have some posters there in the exhibition page, okay? Go there and see the posters. Thank you very much. Giorgiana, do you want to say something?
Thank you, everybody. Do not leave this Zoom link because we will start at 13 UTC, okay? In 10, 15, 14 minutes. Do not leave the session. Thank you. See you in a few minutes.